Hello student, how are you? I hope you all are happy, healthy and fine at home. What did we learn yesterday? Yesterday we learned about the application of or the use of rule of 5 in a carbohydrate that we have learned with the suitable example. I think myoticin, that is one of the example we have taken, how it is applicable, how it is applied there, that we have seen. And now what we are going to learn today, that is again is in that functionalization and control of stereochemistry by manipulation of the hydroxyl group, how we can manipulate this group that we are going to, because we know that carbohydrates are the polyhydroxy aldehyde and the ketone. So polyhydroxy, so that hydroxyl group are playing very important role in the carbohydrate while framing the carbon skeleton. And first one is a steric control, how we can control this. An example of steric control is encountered, means recognized, in the synthesis of an amino acid derived from the antibiotic pyridomycin, that is which is shown in the scheme number 5. We will see shortly, which can be categorized as containing particular hidden carbohydrate type of symmetry, and inspection of the target structure indicates the presence of four different substituents on an acyclic 5 carbon chain with a controlled terminus. And the stereochemistry of hydroxyl containing carbon atom can be considered as the primary preference point with the regard to the nature and the type of precursor sugar to be used. And now let us look at how it is applicable. That is scheme number 5 is shown over here. Scheme number 5. Scheme number 5 means in a natural product, how this is a target molecule. Now let us look at, here is a target molecule, what type of the structure it has. It has, here is a nitrogen atom, pyridine moiety is present over there, and then this is a structure which I am writing over here. Then here is a CO2H carboxylic group present over there, and here must be the methyl group. One methyl group is present over here, and here is a hydroxyl group present, and at this junction there will be the amine group which is above the plane. This is our target molecule. This is a amino acid whole. This is a target molecule. Target molecule, or which is we can call it as amino acid. This is one of the target molecule. And now this, the skeleton, what type of the skeleton may be present over there. Let us look at here. The skeleton is present here like this. The skeleton is present like this. Skeleton is present over here. Here the carbon number starting from here, CO2Me, you can write this is carbon number 2, 3, 4, 5 and 6 over there. Here is a heteroatom, you consider here. From this side is a heteroatom, here from this side is a heteroatom, and then here we can insert that NH2 group from this side preferentially. And this hydroxy group is already there, HO, and now this methyl group 3 I am writing here, and this is a methyl group over here. And now if you do the retro of this, we are trying to find out the chiral precursor over here. What do you get? You will get here this one. Generally here there is a N3 is written here, N3 azide group, and here is a heterocyclic, and this OH can be put here like this. This is here OH, and here must be as a Ame. So starting from here 1, 2, 3, 4, 5 and 6 carbon atoms over there, and this can be obtained from this molecule, can be obtained from this one. So we can, I am writing here O, this one, that is a 1,2 diol. As we know that the protection of 1,2 diol we can protect in this way, and we will get here this one. There is a N3 still there, and here is a heterocyclic ring, not heterocyclic. Here you can bring RO, and here is a methyl group as it is, this methyl, and this can be obtained from this one, this can be obtained from this one. Here O, this is a protected 1,2 diol, this is methyl group, and here we can get O, R, right? Only modified, this methyl group remains still there, and after that we can, this can be obtained from this one. Let us see here. This is protected group as it is, and then this one OR, and here is a RO, and here we can bring as a this, and this carbon-carbon double bond, exocarbon-carbon double bond we can insert, or we can bring there just like by inserting Arvitic type of the reagent, and this can be obtained from D-glucose, as we know that the structure of D-glucose. So this is the target molecule or D-glucose, which is a precursor used for the synthesis of this molecule. The name of this target molecule, which is one of the amino acid. Okay, and it has the same sense of chirality. At the beginning we have seen target molecule and the precursor, what type of the chirality they must have, what type of the functional group, then sense of chirality, then stereochemistry, then functional group relationship, topology, availability and the cost of, these are the things we already discussed in our previous lecture, and it has the same sense of chirality as that at C4 in a D-glucose derivative, and can be protected during manipulation by involving it in a ring formation as in a furanose derivative, and its beta relationship to the carboxyl group allows us to create the later functionality by oxidative cleavage of a diol, thus sacrificing C1 of the original D-glucose. The introduction of a potential amino group as well as the heterocyclic can be easily performed by manipulating the C5 and C6 side chain. And note that the amino group must be introduced with retention of configuration, as we know that retention and the inversion. Retention means whatever configuration, original configuration of that that chiral compound has, that should be maintained, that should be keep as it is. If it has a R configuration, it should remain by introducing that amino group, it should remain as a R. So that type of the thing is called as a retention of configuration. And now hence the necessity for a double inversion process at C5 starting with a D-glucose configuration. The C-methyl, this C-methyl carbon methyl group can be introduced on a suitable keto derivative via Wittig methodology, and the desired alpha orientation can be achieved based on preferential hydrogenation and steric control of an exocyclic methylene intermediate, applying a logical sequence of retrosynthetic steps. One arrives at 1256 isopropylidine alpha D-glucopyranose, hence D-glucose as a practical building. D-glucose is a practical building block, since regio as well as a stereochemical control can be ensured based on well-known chemical transformation. And now the scheme number 6 shows that how it is developed. Let us see another steric control, another scheme for so that you can understood the better way how to what does the steric control is. Let us see, here is a scheme number 6 over here. Now here the starting compound is this one. This is a starting compound where OH, and then here is a hydroxy HO, then here is this one, and there is this one, then double bond, then 1 2 3 4 5 like this, and here maybe as a hydroxy group OH, this one 1 2 3 4 1 2 3 4 is there, and then here similarly this one, and then double bond again 1 2 3 1 2 3 and CO2H 1 2 3 and CO2. This is one of the target molecule that is known as thromboxane B2. This is known as a thromboxane. The name of this compound thromboxane B2. Thromboxane B2, it is the name of this target molecule, and this target molecule we can write this way also. We can write this manner here OH, and that the center is not assigned whether it is above or below the plane, and that's why line is shown like this zigzag. And then we can write this one double bond, then this way there is a OH, and after that 1 2 3 4 bond, 1 2 3 4 bonds, again one more, and now this side there is a bond, then there is a double bond, and after that 1 2 3 and CO2H, and this can be obtained from I am writing here, this can be obtained from this way here, that is there this alkoxy group over there, and OME, it is at anomeric carbon OME OR dash and not here. Here is a OR dash here, OR dash, and that this side, this one, CO2H, H or not H, there is a methoxy group is there. Here is a methoxy group, and this can be achieved, this can be obtained from this one. I am showing over here the group which is like this. All you have to approach, your approach should be as a Chiron over here, and therefore here RO as it is. And now what are the changes I am going to made here? OME still remains as here, OME, OR dash still remains over here, but here this is, I am introducing double bond and then CO2Me, right? So that type of the exocyclic bond we can bring there by using as a this. This is a extended, there extend, and here we can reduce this, and this we can reduce. We can reduce this so that we will get this one, and this can be obtained from this one. This can be obtained from this one. That is a OME still there. Then OR dash remains as it is, but here what is the change we made here? After reducing, we will get RO, and here C double bond O. Carbonyl group, by using as a Wittig approach, we can bring here the carbon-carbon double bond. So this can be obtained from the deoxygenated compound. This is obtained from this one, OH, then one OH above, one OH below, and then this one, as we know, this is a D-glucose structure, and here deoxygenated. This one is a deoxygenate, and this one is a invert. This one is a invert. After inverting, we will get this one. And this is oxidized, and this one is a oxidized. These are the thing. If you do on it, you will get as a your target molecule. This is a scheme number 6. So another example of steric control in the introduction of the acetic acid side chain in a thromboxane B2, which is a drug chemical precursor. Hydroxylation of the olefinic intermediate, this carbon-carbon double bond, by using as a Wittig reagent, we can insert here. So by doing all this treatment, we will get this type of the compound. Now hydrogenation of the olefinic intermediate is virtually assured to occur from the beta means from top side to the to provide the desired orientation of the acetate side chain. So this is all about this. Now is the next one is a steric control or conformational bias, and the anomeric stereo selection, how it is applicable, how it is used, or where it can be used. I think that we will now let us see that steric control and the conformational bias and the anomeric stereo control. I already told you that stereochemistry is playing very important role as far as this in case of the stereochemistry and the biochemistry. Most of the biologies compound are the chiral in nature, and therefore to study this type of the terminologies, steric control is essential to study these compounds. I think with this, let us stop today here. Remaining we will see the next time. Have a nice day. Thank you.